Okay. Okay, thank you very much for the invitation to speak here. Such a nice conference. Unfortunately, I couldn't be here last week. So what I'm going to talk is a relation between, well, at least an attempt to relate gauge theories and integrable theories in on-loop space. Okay. So all the talk will be at the classical level. There will be no quantum mechanics here. Okay. So the main topics I will cover is this feature of gauge theory. So when I say gauge theories, I'll be talking about abelian, non-abelian gauge theories. But the main property I will be using is the fact that the dynamics of classical gauge theories can be cast in this form. As the flux on the border of a volume is the charge inside the volume. And the volume is a three-dimensional volume and can be space, just space, or having space and time components. Okay. The main feature is that such a integral equation leads to a conservation law, which is an isospectral evolution of some operators. Okay, and that's what connects it to integrable theories. Okay. And the other topic of my talk is about integral, not integrable, but integral equations. Okay, and I will construct the integral equations for Young-Mills theories. As you know, electrodynamics was first formulated in terms of integral equations like Gauss' law, Faraday law, and so on. And then Maxwell summarized everything in terms of differential equations. But the Young-Mills theory was constructed a la Maxwell in terms of differential equations. And the integral equation was never really constructed until this result we have got. And this integral equation also solves a long-standing problems in non-abelian gauge, in classical non-abelian gauge theories, of constructing conserved charges which are really gauge invariant. The Noether charges for non-abelian gauge theories are not really gauge invariant. I will comment more when we come to that. Okay. So the next 3 slides will be about two-dimensional, classical two-dimensional integrable theory. So you know it very well. But I have these 3 slides to set the stage to do for what I do next. Okay. So in integrable field theories in 1+1 dimensions, we have a linear problem, okay, which is another way of writing the equations of motion. And the compatibility of this linear problem is the well-known zero curvature condition, or the Lax-Sakharov-Sabah equation. And in the theories that we are interested, soliton theories, for instance, the connection A mu lives on an infinite dimensional cat-smooth algebra. Okay. And then from there, that zero curvature, you have all these methods that we have been listening about, like construction of infinite number of conservation laws, inverse scattering method, Dessing method, errata, classical and quantum R matrices. Okay. We don't expect to generalize all these to any dimension. Okay. But the main feature here is that the zero curvature leads to a path independence of the Wilson line. You know, you have the Wilson line defined on a curve. It's a path order integral. Okay. And if you vary the curve, keeping the endpoints fixed, you get that's proportional to the curvature of this connection. Okay. And when it is 0, it means that W is path independent. Okay. And the path independence leads to conservation laws. And the way you do it is the following. Since the flatness condition leads to this path independence, you can take 2 paths going from the same 2 points. Okay. So for instance, the first curve here, it's a time equals t, and it's parallel to the x-axis, the space axis. And then, or you can go around this way. Okay. Um, since the loop rules on these two curves are the same, and also if we impose boundary condition on the x equals L and minus L, okay, such that the time component of the connection is the same, you get an isospectral evolution, because the operator here is the inverse there, and then the Wilson line on this t equals 0 integration is conjugate to the t equals t. Okay, so the eigenvalues of this operator are conserved, and these are the conserved quantities of integrable two-dimensional theories. And since they live in an infinite dimensional Katsumudo algebra, or a loop algebra that has a spectral parameter lambda, you have an infinite number of conserved quantities. Okay. If you look careful at these conserved quantities and look at the symmetries behind them, okay, you see that they mixed in a non-trivial way internal and space-time symmetries, so they don't commute. And that's no problem, because the Coleman-Mandula theorem in 2 dimensions doesn't apply, so you can have it. In fact, all integrable theories we know of, the charts responsible for integrability have this feature of mixing in a non-trivial way space-time and internal symmetries, and you can do. So generalizing to higher dimensions, especially 4 dimensions, and if you want to keep locality, Lorentz invariance, and unitarity, we don't expect to generalize these things. Okay. So, if you want to go to higher dimensions, what should you do? So, you expect, for instance, let's go to 2 plus 1 dimensions. Okay, you expect the charge to be integrated over surface, a 2-dimensional surface. Okay? That's what you should have. Now, you can, given a surface sigma with a border gamma, you can choose a reference point on the border and scan the surface with loops. Okay, since you have to integrate, you have non-commuting things here, so it has to be surface order integral. You scan it with the loops. Now, the crucial structure here is of loop space, which is a space of functions from the circle to the space-time. Okay, so it's any function f from the circle to the space-time, such that the north pole of S1 goes to this reference point x0 on the border. So it's a loop space based on a point, and that's very important. Okay, you fix this point. But at the end of the day, everything should be independent of this choice. Okay. Now, if you scan the surface with loops, the surface becomes a collection of loops. But loops are points in loop space. So the surface becomes a path in loop space. Okay? Giving a surface, you give a path. Of course, if you change the surface, you change the path. But since this is a space of functions, there are an infinite number of ways of scanning this surface. And each way is a different path in loop space. So you introduce here a huge gauge symmetry, which you don't want, okay, because you have an infinite number of paths corresponding to the same physical surface. And that's a problem. And that's the famous reparametrization invariant problem of these formulations. Okay, I'll comment more about it in a moment. So what you should do then is to introduce a flat connection on loop space. Okay? And impose it to be flat. And if you have it flat, you can play the same games you play in 1 plus 1 dimensions. You have flatness, path independence, conservation loss. Okay? So it's quite natural to think that way. Okay? Now, so you have to implement this. The first thing is to introduce the connection on loop space. How do you do that? Of course, you have to connect to things in space-time. So one way of doing it, and maybe the best way of doing it, is to introduce this one-form connection on loop space. So it's defined on each loop. and involves an integration on that given loop where it's defined, okay? And then you have an anti-symmetric tensor B mu nu, and this is locally defined in space-time. It's given, okay? And you have the Wilson line defined through the usual equation, okay? And that variation there is perpendicular to the loop, okay? And that's what given, that's the exterior derivative on loop space, gives the one-form character to this one-form connection, okay? Here, B mu nu and A mu are not the fundamental fields of your theory. It's like integrable theories in 1+1 dimensions. The lax pair, which are vectors, is a vector, is a connection, is not the fundamental field. It's a functional of the fundamental fields of the theory, right? But there is a crucial point here that we didn't have to add the Wilson line here, okay? We could have just B mu nu. But that's not a good idea, and I think the idea of introducing a W here is Wilson himself, because my collaborator was his postdoc, and he certainly got this idea from there. And if you have a gauge transformation, okay, the Wilson loop transforms like that, so it's the inverse of the initial point and then G, or the final point. And if this mu nu transforms under conjugation, like the adjoint, okay, representation, and BW, I will use this notation from now on. Whenever you have an upper index W here, it means that is that quantity conjugate with the W. W minus 1 on the left and W on the right. So what happens is that this G here, okay, will cancel this G minus 1 that B has, and it's the same on the other side. So the BW transforms under conjugation, but with a group element evaluate on the reference point. So you don't have local gauge symmetry anymore. You have just global symmetry. And that's crucial. This will be crucial to make things gauge invariant, okay, in what follows, and you see. So keep this in mind, that we have reduced the gauge symmetry to something local, at least for this one-form connection. Of course, you can have gauge transformations on loop space, because if you take this one-form connection as a gauge field on loop space, then you can define gauge transformations on loop space. But we are not looking at that now, okay? And this would introduce some huge symmetry in the formulation, okay? So you have defined the one-form connection on loop space. Now, what's the curvature? The curvature is this. It has an integral on the loop, and here is the exterior covariant derivative of this rank 2 tensor. The covariant derivative is this one. It's like the adjoint representation covariant derivative. But you have a double integral on the same loop. This here you have, because this is defined on a loop, so here is just one loop, and you have two integrals on the same loop. And there is a commutator here. Is BW, so everything with the W is conjugate with W, Wilson line, is B minus F commuting with B. And this is in a point sigma prime of the loop, and that's on the sigma point. Okay, so that's a very weird formula, because if you want this to be 0, to be equivalent to the equations of motion of your classical field theory in 2+1 dimension, it's a difficult thing, because this is this F equals 0 on loop space is local on loop space, but it's highly non-local on the space-time, okay? Because you need the equations of motion of field theory to make this to vanish. But the equations of motion are local, and these are not. So if you want to do integrable theories in 2+1 dimensions with this formulation, certainly the theory will not be local field theory. It's going to be a theory of some extend object, like strings in 2+1. In fact, I heard that strings in 2+1 are special. Okay, but that's not what we want to do. Okay, we want to have it as local as possible. In fact, here comes again the Coleman-Mandula theorem, because if you if you accept the non-locality, then the Coleman-Mandula doesn't apply, okay? And then you can have these non-commuting space-time and internal symmetries, okay? So the problems with this formulation is this. The first is the non-locality. There is a huge problem here, which is this reparametrization invariance, okay? Because you can change the scanning of your surface, and you don't want the physics to depend upon it. But these quantities are highly dependent on the reparametrization. And that's a problem, okay? So it's hard to reconcile with local field theories. There are shortcuts. You can simplify things. The first simplification is to impose the curvature of the connection, A, to be equal to the rank 2 tensor. So you kill that term, but then this exterior covariant derivative of the F, but that's the Bianchi identity for F, so it's 0. So B equals F is a local solution for this equation, F equals 0. And there are applications for that, okay? But that kills a lot of structure. Another simplification is this, that we have explored quite a lot. You introduce a Poincare type algebra, which is let's say, a semi-simple or simple Lie algebra generated by these T's. And then you have P transforming under some representation of that algebra that can be any representation, in principle. So if you change the representation, you change the algebra. And P commute, okay? The P's commute. So it's a Poincare type algebra. It's a truly non-semi-simple Lie algebra. And you put the connection A to live on this simple Lie algebra and impose it to be flat. And then the B mu nu, what happens? If F is 0, this term drops. But the B lives on an abelian algebra, so this commutator drops, okay? So you are left with that equation with this, the exterior covariant derivative of B equals 0. That's your 0 curvature. So you impose that on your field equations. So the field equations should be equivalent to that. And there are many examples. The first one is the CP1 model, the Belavin-Polyakov model, in 2 plus 1 dimension. You know, it is a self-dual sector with an infinite number of instanton-like solutions in 2 dimensions. Okay. There is the Skir model, has a subsector which is integrable in this sense. It does have exact solutions there. The charge 1 skirmium is lies on this sector. The Skirm-Fadeev model, I don't know if you know of these models, but also has an integrable subsector in this sense. Okay, and then the self-dual Young-Mills. In fact, these 2 equations here implies the Young equations for self-dual equations. So you can formulate the Young equations for self-dual Young-Mills in terms of these local 0 curvature conditions. Okay, that's what we call local 0 curvature condition in 2 plus 1 dimension, and can be generalized to other dimensions. Okay. Another aspect of this is that it connects to other mathematical structures like GERBs, 2-form connection, higher spin gauge theories. I think you have heard about this thing. GERBs is a generalization of fiber bundles. Instead of a 1-form connection in loop space, you have a 2-form connection, and the fiber bundles associated to these are called GERBs. Okay. So you can find a more detailed account of these in this review paper from 2009 that we wrote with Orlando Alvarez and Joaquim Sanchez-Guilhem. In fact, the original paper that put forward these ideas is from '98, so 20 years ago. So this might work, as I said, in some non-local theories, not local field theories, but in some non-local theories. But we don't want that. Okay? So what do? And this comes a very interesting jump into the argument. Okay? Go back to 2 dimensions. Okay? And have a look. That's why I had those 3 slides that you know very well. Let's look at the two-dimensional case from another angle and do the following. Take two fields. G is a group element, depending upon space-time, which I take as a field. It's not a fundamental field. It's a functional of the fundamental field of the theories. And a connection A on space-time, which is a functional of the fundamental field of your theory. And on every curve gamma, you impose this equation between the two fields. Gx, G at the end point, and G minus 1 at the initial point is the Wilson line along this curve. Okay? So that's a sort of integral equation. Okay? Now, if you change the curve, keeping the endpoints the same, okay, the right-hand side changes, but the left-hand side doesn't, because the endpoints are the same. So, but you have imposed it on any curve. So this equation should hold true. Okay? So this means the Wilson line is path independent, if you impose that condition. But if you have path independence, you have conservation loss. Okay? And that's exactly what we have in two dimensions. Because if you take x very close to xr and Taylor expand this side, you have the Maurer-Cartan form. So and that's, if you expand that side, you have 1 plus a, and here is 1 plus this thing. So the connection should be a flat connection. Okay? So the flatness of this connection follows from this integral equation. Okay? Certainly I'm not saying anything new here, but I'm just looking at the same problem for another angle that gives insight on how to proceed. Okay? Now, so the connection is flat, and another thing you have here is that if you look at this curve as a one-dimensional volume, this integral is the charge inside this volume, and this is the flux on the border. So G is the flux coming out of X, and G minus 1 is the flux coming in XR. Okay? So you have an equation that equates a charge to a flux. And as I said, that's the feature of gauge theories I'm going to use. Okay? So you should look for integral equations in higher dimensions that have this thing. On a given surface or volume or hypervolume omega, you have a volume order integral of some quantity equals to a flux on the border of this volume. That's what we should look for. Integral equations like that. Now, if you look at this thing, it has the form of a Stokes theorem, a non-abelian Stokes theorem. Okay? So we should look for Stokes theorems. Okay? So, you know the abelian Stokes theorems, and you know the non-abelian Stokes theorems for one-form connection. That was built in the 70s, okay, by many people. Okay? I won't give all the references. But let me give you a proof, not a proof, but a demonstration here, which is quite intuitive. If you, as I said, if you vary a given loop where the Wilson loop is defined, the variation satisfies this equation, or that's the curvature of the connection defining the Wilson loop. So let's do the following now. Take a surface sigma with border gamma, and let's scan it with loops. Okay? And let's label each loop by tau, going from 0 to 2 pi. 0 is the infinitesimal loop here, 2 pi is the border. Okay? So you can think of this variation as a derivative respect to tau. And then you introduce an equation for the Wilson loop on a surface. Okay? Because this thing, if you divide by d tau, you get this differential equation. So you get the W at the border integrating this equation, and that is a surface order integral. But the Wilson loop is the loop around the loop here at the border. So the two things should be the same, and that's the non-abelian Stokes theorems for one-form connection, which is quite well known. Okay? We are going to generalize this to 3 dimensions. Okay? But let's give an example, a quite simple example, quite trivial, how to use this thing to have that formulation I just told you about in the previous transparencies. Take, okay, and then when you make it abelian, you get the abelian Stokes theorems. Okay? Take the Chern-Simons theorem, okay? But the Chern-Simons with matter currents, J. And the dual is J mu nu, tilde. What you do is the following. You impose this equation, this integral equation for the Chern-Simons theorem. Now, this equation, you get it from the non-abelian Stokes theorems by replacing f by j tilde here, okay, and impose this equation. Now, so this equation follows from the Stokes theorems, which is a mathematical theorem, is valid for any connection, a mu. And now you use the Chern-Simons equation. So that's the integral equation. And here, again, you have a flux on the border and the charge inside. Okay? And when you take the limit, when this surface goes, just a closed surface, goes to 0, okay, or it's infinitesimal, you get the differential equation for the Chern-Simons. So that's an equivalent formulation of Chern-Simons in terms of integral equations. Okay? It's quite simple, just from the non-abelian Stokes theorem. Now, the flatness condition is trivial because you have a closed surface with, you have a surface with a border. Now you take a surface without a border, like a sphere or like a cylinder. Okay? This means the following. If the surface is closed and has no border, the right-hand side of this equation here, which is on the border, is 1, because there is no border. Okay? So that integral is 1. And so the integral on this path on loop space, which is the closed surface, okay, is 1. And this means the following. If you take this to be the connection loop space, so the holonomy of this connection loop space around this surface, closed surface, or closed path in loop space is 1. But then you section the surface or the path in 2, sigma 1 and sigma 2. Then this holonomy breaks in 2 parts, and then you have that the holonomy on sigma 1 is equal to the holonomy scanned in the reverse order, which is that thing. And this is path independence, because if you revert this, you are going from here to there. And on this one, you are going here for the same point. So the 2 paths linking the same 2 points. So that's the path independence. Okay? So that integral formulation of Chern-Simons leads to a flat connection loop space, which leads to path independence. And path independence leads to conservation law, as I said. Okay? So now let's go back to space-time and draw the closed surface in space-time. So it's a cylinder, but it's not a solid cylinder. It's just a shell, okay, the surface of the cylinder. And the base of the cylinder is on the space, x1, x2. And the height is in the time direction. Okay? So, 2 path is the following. I scan the base with loops, okay? And then I go up on the height of the cylinder, scanning the sides of it. And then I end up with that point of loop space, which is this loop on the top. So that's one path. The other path, I take an infinitesimal thin cylinder, okay, and go up, and then I scan the top, and I end up with the same loop. So these are 2 paths in loop space corresponding to the same endpoints, which is the infinitesimal loop here and the boundary of the disk at the top. Okay? So, the path independence means that this integral is equal to that. So you have the integral on the base times the integral going up. It's equal to this thin cylinder times that thing on the top. And if you impose boundary conditions like the current decays at infinite, because I'm taking this cylinder to be infinitely thick, you see, So, and if it goes to 0 as R2 plus delta, with delta positive, and T some Lie algebra element, depending upon the angles only, then you have that these two things are related by a conjugation. So you have an isospectral evolution. And the charges are the eigenvalues of these operators. So you can calculate the charge as the holonomy on the border or the volume on the book, okay, which is inside the thing. So these are the conserved charges of Chern-Simons coupled to matter fields. Okay. You can do the same thing for Young-Mills in 2 plus 1 dimensions. Okay. So you take the non-abelian Stokes theorems and replace the connection by some fields on the Young-Mills theorem. And the integral equation is this one. I won't have time to discuss this in more detail, but the Chern-Simon example can be applied here. It is the following. That's the gauge field, the physical gauge field of Young-Mills in 2 plus 1, and F is the dual of the curvature of that thing. So the dual of a rank 2 tensor in 2 plus 1 is a vector, it's a skew vector, in fact, and you add it to the connection with a 3-parameter beta here, which can be even complex. Okay? And the Stokes theorem says that the other side should be this, where you use the equations of motion of Young-Mills in 2 plus 1. So that's the integral equation for Young-Mills in 2 plus 1. Okay? If you take the sigma, the closed surface, to go to 0, you get, by Taylor expanding both sides, you get the differential Young-Mills equations. Okay? So it leads to the differential equation. It follows from it. So it's equivalent. These are two formulations of Young-Mills in 2 plus 1 dimension, integral and differential. And it leads to conservation laws like we did for the Chern-Simons. Okay? So the conservation law, in fact, is the holonomy of this modified connection here, okay, depending on these 3-parameter and things. So that's a funny thing. You have a 3-parameter there. It will appear in Young-Mills in 3 plus 1 too. Okay? And you can, in fact, this means the following. If you expand both sides of this equation, integral equation, in powers of beta, you have an infinite number of integral equations. So solutions of Young-Mills in 2 plus 1 should satisfy this infinite number of integral equations. And it does. Okay? We have checked it in 3 plus 1, and it does. I'll give you more details in a moment. I don't want to spend more time on this because I want to go to 3 plus 1. But to go to 3 plus 1, you need the Stokes theorems for a 2 form. Okay, this was not known. How do you do it? You do the same thing you did for the usual non-abelian Stokes theorems. You take a surface sigma, okay, and define on it what is, let's say, the Wilson surface operator, which is quite well known. Okay? So what you do, you take a rank 2 tensor, conjugate by W to have the gauge invariance made it global. Okay? That's crucial. Okay? And you impose this equation. What you do, you take a reference point on the border of the surface, scan it with loops labeled by tau and parameterized by sigma. Okay? So every fixed value of tau corresponds to one loop on this scanning. Okay? And you have this equation, which is the Wilson surface operator. So that's it. You can write it like this, a surface order operator, and VR is the integration constant. Now, if you vary this thing, if you vary the surface, how does the Wilson surface operator varies? Okay? And it varies like that. So you get the same thing because this is the connection I talked about at the beginning, right? This T that I call calligraphic A. So what you get is the integral of the curvature of this connection loop space. So the variation of V is this thing. It has the covariant exterior derivative of B, and then they have this commutator, B minus F commuting with B. Okay? So it's the same thing. But this, look, what I have here is a connection in loop space that I thought of using it 2 plus 1, and I'm using it in 3 plus 1 now. And that's because I played this trick of working with integral equations. That's crucial. It simplifies a lot the approach. Okay? So the idea then is the following. As you vary the surface, so you can introduce another parameter and look at this as an equation for V on this new parameter. And then you get the non-abelian Stokes theorem for a two-form connection, which is this, where left-hand side you calculate through this equation, that's integrating on the surface as a surface order integral, and that thing you introduce another equation, when this parameter zeta, where you scan the volume now, this omega is a 3 volume, okay, with a parameter, with two-dimensional surface based at the reference point and parameterized, labeled by a parameter zeta. Okay, and this we construct this theorem 20 years ago in 98. Okay, on the same paper I just mentioned before. Okay, now how do you do the integral equation for Young-Mills? You use this Stokes theorem. Okay, and that's it. That's the integral equation for Young-Mills, where I have replaced B mu nu, but a linear combination of the field tensor and its dual, the Hodge dual. That's it. And then I use the Young-Mills equation to write that funny commutator in this form. So the B disappears, of course, because the covariant exterior derivative of F, which is equivalent to this equation, gets the dual of the current there. And then you have this commutator, which is now is nonlinear in alpha. You see that have alpha minus 1 in alpha there, beta and beta. Okay. It has a very funny structure. It is a direct consequence of these Stokes theorems I just showed you, and follows from the Young-Mills equation, because I use the Young-Mills equation here. But it implies the Young-Mills equation when the volume goes to 0. Okay? And so it's equivalent. It's an integral formulation of Young-Mills in 3 plus 1 dimension, which is equivalent to the differential, usual differential equation formulation of Young-Mills. Okay? But now you can use it to construct conserved charts for this theory. And here, I'm talking about a truly Young-Mills theories in 3 plus 1 dimension, because this J has the matter currents. Oh, so the Higgs is here, the spinors are here, so all the currents from the matter fields are inside this J. Okay, so you can have it or not, but you can have Young-Mills with a spontaneous broken symmetry through a Higgs field, or not, just have the matter fields, or just be pure Young-Mills like quenched QCD. Okay. Okay, but this is classical, and these we did some on these papers some years ago. And now the conserved charts again comes from the integral equation taking a closed volume. Now the closed volume now is more difficult to visualize, so let's do the following. What I'll do is this. I'll take a fixed point on this room, and I take a balloon, and I inflate the balloon. So fix the time, t equals 0, and I inflate this balloon in this room until the balloon sticks to the walls and the ceiling and the floor. Okay? So what I'll do, I will scan now. This loop here is a two-dimensional surface based at that fixed point there, and I inflate it. So the base of this cylinder is this room at t equals 0. So the base of the cylinder is three-dimensional. Okay? Then I calculate that thing on it. Remember, if there is no border, this side is 1, so that integral is 1. Then what I do, once the balloon has stuck to the walls, I switch on my chronometer and I go up in time with the balloon stuck to the walls. Okay? That's what I'm doing here, integrating in time. When I reach the time t equals t that I want, so this room now is time t equals t, I disinflate the balloon. and I go back to that fixed point there at time equals t. And when the balloon is 1 point, I go back in time. I run my chronometer backwards, okay? And I go back to the same point of the room at the same time equals 0. So that's a closed three-dimensional volume without border, okay? So the product of these 4 quantities should be 1, because that's the volume order integral. So if you impose proper boundary conditions and bring the base point, when you calculate that to the top, you get an isospectral evolution. That's a very important result. It's an isospectral evolution for classical Young-Mills written in terms of these volume order quantities. And the eigenvalues of this operator are the conserved quantities. And look, they are not the Noether currents of Young-Mills. That's important. They're different, okay? So they are not associated to the gauge symmetry. We don't know to what symmetry they are associated. It's a hidden symmetry. In fact, they are different. The conserved charts, they are gauge invariant because of that trick. The thing transforms only on the reference point. So it comes out of all the integrals, so it's trivial. So if the operator transforms like that, the eigenvalue is invariant. If you change the reference point, this operator changes by the Wilson line linking the two reference points, the new and the old one. So again, the eigenvalue doesn't change. This problem we had with reparameterization is also solved because now we have a flat connection in loop space. So if you change the volume, the curve in loop space changes, and if you reparameterize it, the curve also changes. But the connection is flat on loop space, so it doesn't change. So the physics doesn't depend on the reparameterization. That solves a huge problem that people working on higher spin gauge theories and GERBs and all things they have. Okay, so maybe this is the right formulation to that. And it gives non-trivial, dynamical, not topological, magnetic charge to the monopoles of Young-Mills. And it, of course, relevant for the global aspects of Young-Mills. So if you look at the textbooks, the Noether charge can be calculated from the equations of motion like that. You put the commutator on the other side of the Young-Mills equation, and you are left with the ordinary derivatives of the field tensor and its dual. But this, since it's symmetric, these currents are conserved, okay? So the charges are this thing. You integrate the time component of J, which is the electric flux, and this is the magnetic flux. So these are the usual Noether charges of Young-Mills theory, and also in electrodynamics. Now, if you make a gauge transformation, let's take for the electric field, it transforms by conjugation. If this G is not constant at the surface at infinity, it cannot come out. But if it is, it comes. So then the eigenvalues are gauge invariant. Okay? But here, it's not the eigenvalues which is constant, it's the operator that's constant in time. It's too much. Okay? You cannot have the whole operator being constant and being gauge invariant at the same time. So in our case, it's the eigenvalue. So only the abelian subgroup gives conserved quantities, not the full group. So the number of conserved quantities is the rank, or depending upon those parameters, is more. So if you take the Wu-Yang monopole and the Truft-Polyakov monopole, at infinity, they are the same. And our chart can be calculated by surface integrals or volume integrals. So they should be equal. So the surface integral for Wu-Yang and Truft-Polyakov are the same. So our charts are the same for these two monopoles. And a crucial property here is that when you conjugate the field tensor with W, this quantity here, that's here, R scalar T, it goes back to the reference point. You see, it disappears. So you have a Coulomb field in the direction of one U1 generator, which is chosen when you choose the reference point. But as I said, everything is independent of this choice. So if you change the choice, you change that U1. But the charge will be the same. Okay? is the eigenvalue of this operator. And if you use the integral Bianchi identity, that should be 1, and you even get the quantization. But these are dynamical charts, not topological. So you get quantization here, even for dynamical charts at the classical level. Okay? And the textbook charts calculate on this monopole is 0. So the Wu-Yang monopole doesn't have any magnetic charge from the Noether chart or for topological. And the Truff-Polyakov has only the topological. But this dynamical one is the same for both. And it is not topological. Okay? And it solves a long-standing problem in classical Yang-Mills theory of constructing conserved charts, magnetic and electric, which are really gauge invariant. So the message is, if you want to go to higher dimension, construct integrable theories, maybe you should look for integral equations of this form, which looks like a gauge theory, because it equates charge to the flux. Okay? And I showed you that integrable theories in 1+1 dimension can be seen as a gauge theory, okay? Because the Lax equation can be written as flux equals charge, as I showed you, okay? And I finish here because Alcaraz is already killing me, okay? He'll delete me.